Hey, I should grab my mic and put it on the cart too. Okay, we're going to start with 4.1.3. I want to do a bit of an exercise with you guys because this is mostly review of what we did long ago before break. So what we should do, let's partner up. Sydney, would you mind working with Lucas for this one really quick? It won't be a big deal. You guys can just do an ABC. I think that would be ideal here. Okay, so this is just me forcing you to talk to each other. So I understand the resistance to that, but I think it's a good idea because I can just tell you what's going on or and give you a chance to actually think about it. Here there are 4 problems that you already know the answer to. No. It's okay if you don't. It's okay. You'll get a chance to look at them in a moment. I think you'll be surprised how quickly that comes back to you. So for each expression, what you got to do is you want to draw and shade the region for a generic function. You probably want to do this maybe off to the side because it's going to get a little busy if you try to do all 4 on that one drawing. So maybe do them off to the side a little bit. And then what you want to do, really I'm interested, is simplify each integral expression and summarize each case on your paper. Let's do A together, just as an example here. So all we got to do here is we're talking about the integral from A to A of f of x dx. So off to the side here, I'm just going to quickly sketch a picture of what that would look like. This particular function doesn't really matter too much, so it doesn't have to look the same every time. But if I'm looking for the integral from A to A, I mean, there it is right there. It's just that little rectangle right there. So the picture is done. And the question is, what's this going to be worth? How could I simplify this expression? What is the area under the curve from A to A of that function? And we talked about this one a little bit last time we were together on Tuesday before Christmas, but the answer to this is 0. Because you can see that there is actually no actual width there from A to A, so there's nothing there. So it's going to be 0. And by the way, I'm going to pause right now and fast forward to the end of today. At 4:30, what we're really going to do today is we're going to build kind of a list of rules, general formulas for all the properties of definite integrals that we're going to discover today. And that's one that we could probably write down right now. The integral from A to A of some function f of x dx is always equal to 0. It's probably the first and easiest of the integral rules that we could be aware of. Now, for this exercise to work, you have 3 left. So there's B, C, and D. Let's call them A and then B and then A, or in the case of you guys over there, it'll be person C. I don't really care how you decide who's going to be A and who's going to be B. However, I think what should happen here is that the person A and person A is going to be explaining this. And what I want you to do is to pretend like person B, if you're person A, on question B here. This is a lot of A's and B's. It's very confusing. If you are, I'm looking at question B, if you're person A, I want you to pretend that person B was not at school at all on Tuesday when we first talked about this. Maybe you were, maybe you weren't. That's actually a legitimate case that might have actually happened here. Try to explain, that's the kind of pretend that you want to do here. Pretend that the person was not here. Explain to them why the rule is what it is and why it would work out the way it is. You want to draw a picture and you want to summarize the integral expression for what's going on there. I'll help you out a little bit on these and kind of give you a bit of a push in case you're completely forgotten what's going on. I'll help you out a little bit with these. B, with C, I don't really know what I can do here. I think I might just highlight this right there, maybe as a hint. And actually, I don't know really. D, I'm not really sure either what I can do here. A to B, okay. Interesting. Okay, anyway. We'll talk about D together when this time. We'll take about 5 minutes for this, I think. So let's at least try B and C, where so person A is going to explain to person B how this problem is done as if person B was not here, and then you're going to switch roles. Person B is going to explain question C to person A as if they were not here. Does this kind of make sense? This is just me forcing you to talk to each other about math problems. I'll give you about 5 minutes to talk about it, and then we'll debrief the answers. Sound good? Okay, go for it. I'm going to put some snow boots on because I did not bring shoes today. All right. He said that person B was. Yeah, no.
in every single one, I flipped these, which is good to know because it means that my brain is backwards on that. But it's also unfortunate because it means my brain is backwards. Every time I write it, I write.
So I'll help you guys out over here. So with 427 part B. So what you want to see is that if you look at the picture here, the area from A to B, together with the area from B to C, you would just be able to combine those two areas together. So it would just be the area from A to C of f of x dx. I'll take squiggly line.
And in the future.
Remember, it's just a big capital letter S. It stands for sum because you're adding up a bunch of
Oh,
rectangles.
yeah.
There you go. That's true. It's all coming together.
Yeah. I don't know why.
Is the top one the top one?
Yeah, I think isn't the top number the second? It would be the
Bottom
second.
number is the left, and top number is the right.
What? I'm not on my chapstick.
Guys, put on chapstick so
Yeah, same. I'm with Jeff on this one.
No. You do it normally.
Well, I literally do the same thing.
No. You did not.
Why? Is it because it's pink?
It's nothing to do with color.
Oh, my chapstick's nothing wrong with it. No,
Good conversations happening. Glad to hear you guys.
Maybe. We skipped it every time we had the problem before. We just skipped. It's either one or it's, I don't know.
Oh, because it's.
It's left going right or right going left. That would be the same thing. Maybe it's just because you're going from A to B, or no, you're going from right to left. So from B to A plus A to B. So the B times 2.
Wait, hold on. If the top is the right end point, and the bottom is the left end point, how would it
Wait, yeah.
Then we talked about this a little bit. Way back on Tuesday. If you flip the order, that's right. If you flip the order around, well then this is actually exactly
opposite.
yeah. Then the whole thing becomes negative.
Oh, okay.
You start reading it from right to left instead of from left to right, and the whole integral becomes negative. So in that case, the integral from A to B plus the integral from B to A, they would be the same area but opposites of each other.
You understand? So you understand where I was going with that,
Yeah.
right?
Yeah.
The cycle, right?
Go team! Go team! You guys did it! You guys did it! You guys are awesome!
I still
What's his name? I don't remember what it.
Question C. I'm not
No. Yes,
I know. I have to get my hoodie back.
I know what it is. I just what was the kid's name?
So out of nowhere, it was weird. I thank you for
Was that no, Christopherson was normal. He got the bow. Looks like a bear. Did you say Christopherson's a girl?
That's it's okay, which one would be the line? Are they married? I don't know. Yeah. Well, you can do it. Oh no.
I got nothing else to say.
Yeah. Honestly, I would say I would rather get
We got about 20 seconds left. Can I get you guys back up here? Let's. I think we're all kind of in agreement about B and C at least right now. It might take a minute. It might just be a good idea for us to just visually review. I kind of drew a picture over there on the board. The best picture I could draw in a quick little second there. The idea here is that we're measuring the area between the curve and the x-axis by taking that area and chopping it up into several small rectangles. And then we're adding those areas all together. The rectangles are, I kind of drew them with little vertical lines on this picture. The idea is that the rectangles we're chopping that area up to are very, very, very thin, infinitely thin. The word we use in calculus is infinitesimal, which is the same idea as infinity, but like infinitely small. So it's infinitesimal is kind of the opposite of infinite because it's like infinitely tiny. But if you were to zoom in on any one of those rectangles, maybe like pull it up and blow it up a little bit, it would just be a rectangle. And its width would be this thing we call dx, which just kind of means a little bit of x, a little bit. And its height would be f of x, just whatever the function value happens to be at that point on the curve. And then that's where this notation comes from of the integral from a to b of f of x times dx. Don't forget f of x times dx is just length times width. Whenever you guys are ready, you can join us, please. It's okay. So f of x is the height and dx is the width. So you're really just adding together a bunch of areas of rectangles. So far there are some big takeaways. These three rules are probably the most important ones to know right now. The integral from a to a of something is just going to be 0. On question B, you can combine together two adjacent areas. What happens is you go from a to b on the first integral, and then from b to c on the second integral. So since they both kind of stop and start at b, you can just combine them together and call it one integral from a to c of f of x dx. The third rule is one that we kind of played around a little bit. I'll zoom way in on it, make it nice and big there. The idea there is that the order of the integrals got switched around. Actually, I want that thought bubble trail not from this one. I want it to come from this one. So I notice that the first one is the integral from b to a. So we usually say the left endpoint on the bottom and the right endpoint on the top, because we always travel from left to right when we're thinking about things on the x-axis. Integrals are the same thing. You go from the lower endpoint to the upper endpoint. So what do you do when suddenly they have this weird backwards relationship? Well, you can just flip it. You just put the negative sign in front, and the integral now goes from a to b instead of b to a. What that means is that these are both the same area, just one of them's negative. And so they cancel out and become 0. D is one that I'm not sure we've talked about yet. So let me do my best to also play teacher for a moment and try to explain what's going on in D. I'll give you the answer really quick. It's a really easy answer. The answer is that constant k. You can just kick that out in front of the integral. So this is equal to k times the integral from b to a of f of x dx. Make that a little more a-like. There you go. That's the answer. That's the end result. And if the end of this conversation means you just memorize that rule, hey, I'm a happy guy. I don't care. But we should at least talk about why that rule works. This constant k. So what we're doing here is we're taking the area of f of x dx from b to a. Again, I don't like they've gone from b to a, but hey, what are you going to do? Let me get rid of this drawing here really quick. So the area from b to a is all these little tiny blue rectangles that I'm drawing here. I'm just adding a bunch of blue vertical things there. That's the area. So what would happen if instead of this being f of x, what if it was k times f of x? What if it was some constant? What that would do is it would impose a vertical stretch or a shrink on the graph. It would stretch the graph vertically. And let's just say, for example, that k was 2. What if this was 2 times f of x? All that would do is take any point on the graph and kind of double it. So this a would now become 2a up there. And this b here would now become, this is going to be a little bigger than I want it to be, 2b down there. And the graph would otherwise follow the exact same path. This would still be 0 right there in the middle. You'd have pretty much the same path, just like doubled in size. And I just pick out 2 as an example to show you. K could be anything. K could even be a decimal, and it could make it smaller. What's going to happen to the area, though, is the area is going to follow that exact same transformation. It doesn't really look like it on this graph. It's not super clean. But the area of that new times 2 stretch version is just the same blue area times 2. So the idea is that if you just double this area here, this highlighted yellow area that I'm circling right now, if you just double that area, you'll fill in the empty spaces that we just added by multiplying everything by 2. So the rule ends up being that if you multiply by a constant inside of the integral, right there, you can just kick that constant outside and put it in front. So far, let's skip to the end here. Let's skip to 430. Because the ones we've talked about so far are actually probably the most important ones. We've got kind of, I think, 4 different rules that we should mention. The first rule is that if you have the integral from a to a, it's just going to be 0. The next rule is that the integral from a to b, let's try this again. Let's do the integral from b to a of f of x dx. This equals the negative integral from a to b of f of x dx. Again, the only thing that changed there is that we changed the order. Instead of going from a to b, we go from b to a. And in order to do that, we have to make the whole thing negative. Really common AP Calc questions dealing with this kind of stuff too. Very similar to this rule is the one we looked at in question D. If you have the integral from a to b of some constant k times f of x dx, you can just take that constant and kick it out in front and deal with the integral and then later on apply that multiplication. We have kind of the same rule for derivatives. The integral and the derivative really aren't interested in the constant in front. So you can just ignore it and put it out in front like that. And then the last rule we had was kind of the combining of things. If you have the integral from a to b of some function f of x dx, plus the integral from b to c of some function f of x dx, well, you can combine those together and make it one integral from a to c. And it's nice to have integral notation because remember that this is filling in for that old sigma notation that we used to do with all those little rectangles and the limit as n. I'm glad that we're kind of done with that stuff. Integral notation is much easier to deal with. It's much cleaner. It's much more descriptive of what's happening. And the more we practice it, the more you get used to reading it and thinking about visually what's happening as you read the notation, which is a big part of upper level mathematics. So far, these are probably, this is I would call this the big 4 so far. We got rules 1, 2, 3, and 4. Not that they are always going to have those names, but we have 4 rules so far. These are really, really common things. But I want to explore a couple other really common ideas today. So let's move on. Let's go back in time a little bit. Let's go to 48. I would like, or sorry, not 48, 28. 428. I would like to do this problem together right now. This will be a good review if you weren't here on Tuesday, or if it's just been a week and a half since you even thought about calculus. This will be a good chance for us to get a handle on what we're doing so far. I should point out that we do not have any tools in our tool chest yet to work with integrals at all, except for area. That's the only thing we have. So all the problems today and the ones in the homework can be done by just drawing a geometric shape and using like a triangle or a trapezoid to find the area. So that's going to be the case here. So what we're going to do is we're going to investigate the following relationship of, notice what's happening here. We have the integral from a to b of f of x dx plus the integral from a to b of g of x dx. This time we have the same bounds, a to b, for both integrals, but we have 2 different functions, f of x and g of x. If I was going to try to draw maybe a little sketch, you don't have to draw this with me, but if I was going to try to maybe make this happen, there's a and maybe this is b. Let's say that f of x was this blue function. And what if g of x was maybe this green function? It's kind of like how would we deal with the areas under those curves if we had to add them together? Something like that. It's, despite this picture, this is a bad drawing. It's surprisingly easy, but here, let me show you. Let's look at question A. This will give us a chance to practice evaluating integrals based on just geometry. So for question A, we're asked to evaluate the integral from 0 to 2 of x dx and 3x dx. So let's draw both of them on the same coordinate axis. You can do this with me right now. It's pretty easy because they're just like lines, straight linear functions. We're going to go from 0 to 2, so we only need to mark out, on the x-axis, we only need to mark out 0 to 2. 0, 1, and 2. For regular old x dx, that's just going to be the function f of x equals x. In this case, it might be useful to just note down that, okay, f of x is just going to be the function x, And g of x will be the function 3x. So for f of x, it's just the graph of y equals x. So here's 1, 2. I'm just going to put a point here at 2, 2. And there is the first function right there. So the integral from 0 to 2 of x dx is just going to be the area of this triangle, which is 1, I think. Yeah, because if you do the area formula for a triangle, it's 1/2 times base times height. Base is 2, the height... Oh, no. Sorry, I miscounted. Base is 2, the height is 2. I have different scales going on here. So this would be 1/2 times the base times the height, which is just going to be 2. That's it. The other one is going to be about as easy. I mean, first of all, if you're following along so far, you could take this constant of 3 and just kick it out in front and then do the same integral but multiply the answer by 3, but that's not the point of this problem. Let's see, 4, 5, 6. If I were to plug in 2 into 3x, I would get 6. So the g of x function is going to look something like this triangle here. That triangle has the same base of 2, but this time it's got a height of 3 times 2 is 6. So the integral from 0 to 2 of 3x dx is the area of that blue triangle, 1/2 times the base of 2 times the height of 6, which in this case is going to be 6. Which, of course, you could have used that constant multiplier rule and just taken the 3 and multiplied to get 6 also. You could have done that. It's okay. You don't need to do that. So, as far as question A goes, A wants us to take those two integrals and add them together. So 2 plus 6 equals 8. I think that's worth writing down up here in this space. 2 plus 6 equals 8. That would be the final sum of those two integrals. Now, I don't know how meta you get about your math education and your math classes that you take. I don't even know if you guys know what the word meta means. But maybe you can kind of see. It's kind of like do you see what I'm trying to show you with this problem? Maybe that's a good question to ask. Do you see what I'm trying to show you? If you add together x and 3x, you get 4x. So the objective here would be to show you that the integral of 0 to 2 of 4x is just going to be what we just calculated in the previous problem, because that's just adding them together. And it is. Here, we'll do it right in the same coordinate grid. I have to scrunch it in a little bit. It's not going to fit quite. 7, 8. It's going to be up here. But this would be 4x. And the area of that red triangle would be kind of the same thing. It'd be 1/2 times the base of 2 times the height of 8, which would be 8. And it ends up being the same answer as the sum up above. So what we get at here is that in question C, we can easily rewrite this expression if you're following along with what's going on. And even if you're not following along, you can just write it down. If you're like the kind of person that likes to memorize stuff, hey, that's okay. That's why I like CPM so much, though, because I memorized my way through a college math degree. And now I kind of have to sit here and think about, like, why does that work? The thing I memorized and spat out time and time again. So all you got to do here is take those two functions, f of x and g of x, you can add them together. This would be the integral from a to b of f of x plus g of x. And we would want to put that in its own set of parentheses, since it's technically going to represent the height of a rectangle times the width, which is just dx, like that. And we're going to add this to our list down in problem 430. We might have already done that if you're an overachiever. Or even a regular achiever. So in this case, you have the integral from a to b. I'll zoom in a little bit closer to this one. If you have the integral from a to b of f of x dx, plus the integral from the same bounds, this is important, the bounds have to be the same, a to b, of some other function, g of x dx, you can combine these together. You can make it one integral from a to b of, in parentheses, f of x plus g of x times dx. We'll call this rule number 5. Again, the philosophy, like most things, the philosophy in this class has never been to be like, expect you to have mastery of something on the first day. It's just like you see it today, and we'll keep seeing it in homework problems and future problems over and over again. And it's cool the way things are starting to pay off. I was a little nervous there in chapter 3, but I'm looking ahead at like chapter 4 and 5, and I'm like, oh, this is going to be cool. This looks like a lot of symbols. Yeah, you want to fill up mine too? Actually, I don't have mine, do I? You can fill my kettle up though if you want. That teal can will be fun. That would be cool.
She's dying.
Ooh.
Sorry for my cups over there.
I don't have any cups now. There is a bottle of mysterious liquid over there on my heating register. I'm not sure.
Those cups?
What are they?
Those are favorite cups.
What?
Jeff, tell me
Oh, Jeff, I don't know if I trust that.
Jeff,
Oh,
get a cup.
we have cups. Advisory, man.
From advisory.
They're
Am I allowed to steal?
amazing. Hey, thanks, Kara.
I didn't-
Just walk it over here to him.
Do you want your kettle? Fill up too?
Yes, please. Let's look at 429. That'll be our next and last destination day. I'm going to give you guys a chance to explore these a little bit. I'm going to give you about, I don't know, maybe like 10, 12 minutes or so to really explore these. Here is the thing. These are not as easy to see as the other ones, so they might include a little bit of guess and check and some pretty intricate drawings. But what you're looking for is looking to examine what happens to the area of a region when a function is translated. In case you haven't seen the word translation in a while, what that means is a slide. Yes, geometry time. Means you don't flip it, you don't rotate it, you don't stretch it, but you just take it and slide it somewhere else. Here's the deal about there's 4 situations here, A through D. One of them is true. The other 3 are not. So I suppose you could play this as a game of find the fiction for a little bit. Only one of these is actually true. So if these are all does questions, does this thing equal this thing, explain why or why not. 3 answers are no, and one of them is yes. I'll give you that as a little bit of a push out the door. So take a look at the picture. Talk to each other a little bit. I don't have a structure for this. Just think about it for a minute. And I'll be back with you guys in about 10 minutes. How's that sound? That'll be good. Perfect. I'm going to delete this timer. And if you're watching this video after the fact, feel free to skip ahead in 10 minutes. I'm not going to stop it. I'm just going to let it keep going. That shows up on the homework questionnaire. Stupid taste in this. Wait, we didn't have to, not to make it, but like, not to spoil the adventure. Yeah.
It's like I'm alright, I didn't go get my water.
Yeah, sure.
I think she teaches together.
Very slim line. I've only seen one.
I barely saw the other one look too.
tell you that Miss Kenny texted me during 4th hour telling me that she believes he's still in class for wearing full camo.
Wait, what happened?
I feel slightly responsible.
Wait, so Easton wore the ghillie suit to her class, so she kicked him out.
Well, he also said the F word many times. No, this is all according to text.
Well, okay, I mean, I believe Easton with the F word.
Whatever that suit that he was wearing,
The ghillie suit.
he wore it to
We're all like,
Kenny's.
hey,
Why was he wearing a ghillie suit?
He went to Kenny's 4th hour and she booted him out of class for it.
Who brought a ghillie suit?
It's that ridiculous
The
camouflage.
same guy that Mr. Olds yelled kicked out for throwing that
He's,
pencil and disturbs his class too.
The thing is, like, I don't know what I did right. He's never been rude to me at all.
tell him wrong
He's never been.
Isn't he the one who gave you the Christmas present?
Yes, the banana Twinkies.
I don't know why he likes me. I hear
Probably
horror
because
stories.
he thinks
Other
you're
classes, I
better
hear
than
horror
us.
stories.
I don't know, I feel like he just doesn't have freedom in all of those other classes except advisory. And if you have one other class.
He's also in my 6th hour alcohol, which is like historically.
So why did I miss? No.
Ooh, that would make
Nice work.
much
Yeah.
more sense.
It would make a lot of sense if you guys told me what 3 seconds.
I don't know.
Excuse me, sorry guys.
These two are right. Oh, by telling you that I kind of gave away.
Yeah, you
Three
did.
of them was
I know
those are
they're
actually first of all.
This one is just moving the bounds, but not moving the function at all. So if you were to slide the bounds A and B to the right,
C
C
number
A's
steps,
wrong, but not change anything else, you'd be looking at a whole different section of under the curve.
Why'd you erase it? Oh, never mind.
I erased every single other one.
Where are you guys right now?
Your mom's house.
Oh, I didn't
Oh,
question.
you're lucky I'm cool. I could boo you out so much so many times for so many things.
On this one,
But it hasn't happened yet.
like you multiply this by this, that by that, that equals 2 by 6.
Yeah, in this case, yes, that works.
Okay,
in
that's
this
just
one
a
case,
coincidence.
just do one, yes.
And then K2, that's just a coincidence.
Yeah, just a
Okay.
coincidence. I like that. I like that you asked the question you asked.
I think that's
I have this kid in my 6th hour class who like comes up with these like, so he'd probably be like, so it looks like if all I do is just this and this, I'll always get the right answer. And I'm like, I don't think so.
It's the one D kid with the red hair.
No,
Not him.
different kid. He's
Oh,
always
no,
like,
he
and,
was
his, and I know we're not supposed to compare siblings, but his brother was the same way. He just like will see patterns that aren't necessarily there. Sometimes they are, but sometimes they're not. He'll be like, oh, I get it. All you do is multiply those 2 numbers, and I'm like, no, I mean like that works in this problem, but that's not. He's always looking for the. He's always looking for the shortest possible way. I'm gonna go ahead and stop this 5-minute time since you guys are all there. Let's just briefly talk about which ones these are. The one that is true is C. But let's talk for a minute about A and B and D and why they don't work. So the problem with A is that you have the K kind of inside of this parentheses, and that's not really a thing. This problem A shows up on the homework in problem 432, I think. It's the second problem on the homework. You'll see an example of how that should work. Let's just draw a picture of it really quick, though. If I were to take this, let's take a look at this area here. If I were to take that area and add K to it, what would happen is it would all slide up. It would be a vertical translation. It would move up K number of spaces. So now what I would have is like, I'll try to draw, how about like this? It would look something like that green graph. The problem, though, is that the area under the curve now also includes all this stuff down here. So you don't just add on K. You have to add on K times the width of A to B. You have to add that whole rectangle on there. So you do have mostly the same area in that greenish section, but you have a whole other rectangle that you've added to the picture also. So to make this correct, it would be plus K times B minus A. You'd have to have a width on there too to make it work. But we'll talk about that later on in question 432, which we're going to have some time to talk about, I think, today. So question A is a no. Sorry. Question B is another fun one to draw really quick to explain why that one doesn't work. If you understand what it's saying in question B, it's taking the same integral of the same function, but adding C to the bounds. Take A and B and just slide them both to the right some number of steps. The problem with this is that it doesn't move the function at all. The function stays right where it is, and the bounds move. So let's just say, for example, that let me extend this curve out a little bit. to help draw the picture of why this doesn't work. Let's just say we decided to move A and B to the right. Let's say maybe there and there, like that. This is now, that is A plus C, and that is B plus C. All we did was slide the bounds to the right, some number of steps. The problem is that now we're looking at an entirely different section of the curve. There's no guarantee that's going to be anything even close to what the original section of the curve was at all. So that's not the same thing. However, if you look at question C, which is the one that's correct, here's what question C does right. It moves the bounds, A plus C and B plus C, and then it also moves the function to match. So this slides the entire thing to the right. Question C would be like if I took this area here that I'm going to circle in blue. What if I took that and slid the whole thing, maybe, I don't know, that many steps to the right? It would look something like this. It would still be the exact same shape, just somewhere else. You don't see these kind of problems very often, if ever, but it is a thing that does exist. If you move the bounds to the right, then you have to move the function also. Don't forget that f of x minus c means a translation to the right. Similarly, in question D, this is to the left, so we'll talk about that in a minute. So doing x minus c moves the function the same amount of steps to the right as you moved both of the bounds. So everything is still the same. This is a hard yes. And then question D has kind of the opposite problem that B has. It keeps the bounds in the exact same place, A and B, but it moves the whole function to the left. So this takes the function, slides to the left, but leaves the bounds right where they are. And that would not give you the same area. It would be a whole different section. Kind of like question B, it'd be a whole different section of the graph. So it's not the same thing. So let's add one more list to our, for 430, for our list of rules, let's add question C, because that's pretty much the same thing. You can take an existing integral, let's call this rule number 6. You can take an integral from A to B of f of x dx. Take that existing area under the curve, and what you can do is you can slide the bounds, let's say c steps to the right. Or to the left. You can make it minus c if you wanted to. A plus c and b plus c. But if you do this, you have to also slide the function the same number of steps to the right. So you'd have to have it be f of x minus c dx inside that integral. That would give you a horizontal translation of the same area under the curve. Pretty cool. There are a lot of other examples to look at later on in the class, but for now, I should point out that we've made it to the end of the first part of Chapter 4, 4.1. The goal was to get Chapter 4 done by the semester break. We might still get there. So 4.1 is complete. We did 4.1.1 all the way through 4.1.3, which is where we are right now. There is a quiz for 4.1. I was going to do that tomorrow after we have a chance for some homework Q&A and get any other last-minute questions out of the way. And then we might start looking at 4.2. Who knows? We'll see where we are at that point. Well, I'm going to keep, like I said before break, I'm going to keep pushing the schedule forward. I mean, quizzes, I'm more interested in those being like group efforts. I don't want you to be worried about grades, but I do want to keep looking at more stuff. I'd rather have us be worried about understanding the material than worried about what grade we're going to get on things. And speaking of which, I'm like 4 weeks behind in this class, so I took a bunch of stuff home, didn't look at it.
Oh, you didn't?
Oh, sorry. No. Speaking of which, if you have your Chapter 3 stuff, and you want to turn any of that stuff in, that would be a good idea.
It's alright, trash.
It's okay. That's all right. The homework is everything except for Part B of problem 434. Perpendicular or normal lines have not been on the AP test for some time.
Watch. This year?
Yeah, they won't be. They won't be. They've been gone. They've been long.
Everything except for what?
The question B on 434. I mean, it's the exact same thing as the regular equation of a tangent line, except for you use the perpendicular slope instead of the, who cares? Used to be way common, now they're not. I did make a video of this, but I haven't uploaded it yet, which is what I'm going to do right now. And then maybe we'll close out by looking at 432 together. How's that for a slice of fried gold?
You want to
That is, yep, that is the derivative.